end to the inverse problems course. As usual, you know, the story is that we consider the situation where we have a measurement m tilde from some device. Today, the device will be this one, a camera. Then we have the so-called Continuum model for kind of description where this vector came from. And the Continuum model we write in this kind of form. We are considering linear models with a linear operator A beautiful. There is a function f beautiful. In this case, it will be a function of one real variable. Not two, although the camera is taking two-dimensional pictures. We are just considering one row in the picture. That's why actually we are looking at a function f, which is kind of how much light is coming to one point along a horizontal line in the image. That's f, and inevitably we will have some noise, and we will record data with a couple of different noise levels to also get some real-world noise to our measurements. But the Continuum model in our case is, you may remember how we were talking about misfocusing a camera. So what happens if we are taking a picture of, let's say, this kind of a dark surface where there is just one bright spot. If we focus the camera perfectly, we get a picture with a very small dot there. However, if we misfocus to a good approximation with many optics, it happens that what we see is actually a disk of constant value. And this we will take as our assumption, what happens when we take a blurred photograph. But we are not taking a picture of a point, because like I said, we want to be dealing with a function of one variable. So we'll take pictures of stuff that are constant in one variable. So one example picture we are looking at is something that has bright color here and a very sharp drop here to dark. And then we misfocus this one. So what happens is we will get some blurry area between here, and we are just looking at one line. So in a perfect world, we should see something like this. But when misfocusing, we see something like this. There will be that kind of a process going on. And so here, this jumpy function with a real edge and discontinuity, that would be f beautiful. And m tilde actually is, there is first of all, there is this blurring thing for this function happening with this disk, but the disk will have the disk moving here, so because of the constancy of the picture in this dimension, we are actually observing this kind of one-dimensional happening. And what is the point spread function here in the 1D situation? It will be, the value of the point spread function is the area of the disk up to some point, like we discussed a while ago in the course. So and that's why we built our one-dimensional convolution model with the specific form of point spread function coming from these areas. So now we are using that assumption here. So our A beautiful operator will be convolution, continuum convolution, with a function like this that records partial areas of a disk. That's A beautiful. But then m tilde is in RK, so we should have just a finite number of points. Well, the camera has a certain number of pixels. So along this line in the image we take, there is a number of pixels, and actually we are not recording this function at all values. But only at some and those are our m tilde. That's why we have just k of them. And then the camera will have some noise as well, so we don't have the perfect infinite precision values of this smooth function here. We will have some error in them. And also, actually, of course, our A beautiful operator described by this one, surely it's not a perfect model of what happens inside the camera. For sure, it's not completely accurate. However, that's what we use. And then we have the computational model to be able to somehow reconstruct f in a finite form. So as you remember, we designed this kind of model where A is a k by n convolution matrix, and in the rows of A there appear point values of this point spread function. And we built this in the way that if f vector, so this is a vector in Rn, if this vector represents point values of f beautiful at the same points than m is given, then multiplication by this matrix should give closely the same k vector that the camera gave us. Okay, so that's kind of the background story, what we used to do. And the A matrix in this case is square, so actually we will have k equals n in this case. And as you may remember, the A matrix had these values. So if I point, see, this is the middle value, so it looked something like this. That kind of thing. So today, let's record a couple of data vectors like this. We'll do it with a little bit less and more misfocusing, so we get different sizes of the disk. And also we will use different ISO settings. As you may know, with the camera, if you have a lot of light, you're shooting photos in bright sunlight, you may take, for example, ISO 100 in the camera, because then you get a lot of photons coming in. But if you are shooting pictures in kind of a dark room with poor lighting, then you might set the sensitivity of your camera up, maybe up to something like this. So then it's reacting to much lower light levels and giving the picture. But that will result in more noisy pictures. I'm pretty sure you all have experience with this kind of thing. Maybe not all of you have really consciously adjusted this number in the camera. But anyway, when you take pictures with your smartphone, if you take them outside, you see they are high quality and bright and nice. And if you are in a dark lit cafeteria or something and you take a picture, it's kind of grainy or noisy. It's because of this kind of thing. There are less photons coming in, so the information is more noisy. So today, deliberately, we will take pictures with different settings, so we'll get more noise. And let me show you my objects I prepared for this. Carefully stored in the Hello Kitty folder I got from a Japanese department store, Takashimiya. So we have this one with a sharp sharp drop in intensity and some. Okay, so this one, and then to make it kind of interesting, this is an EAN code showing all the numbers possible in the code. So let's try to recover this code from the picture. And for added delight, actually I think we should add here a little dot to give us some idea how big our misfocusing is. So let's add that. Let's just put a small dot. So now we have a little disk. Oh, we even have some pins here. And any questions or comments at this point? Sarjan.
So we don't include any model of the noise in the computational model. We just assume that it's small enough that we can get close.
Yes, so a model for the noise. This is an excellent question. Right now here we are just assuming that this is a small or smallish vector, and we don't really study the structure of the random noise. That's actually more the topic of the course Bayesian inversion. That's kind of every other year compared to this one. There we do a more careful statistical analysis of this one. But here we actually mostly just think that this is a vector whose size estimate we roughly know, but otherwise we don't know it.
Yes.
Yes.
Yeah, I just have some difficulties, with this RK and then this model, because you say A beautiful, F beautiful. Where does the K come from, that model? 'Cause that's like a continuum model. That's still, yeah.
So it goes like this. So we have this F beautiful defined from R to R, and then this AF is a function also defined for all real numbers. So here x equals belongs to R, and this is defined by integral like this. So we have here the point spread function, and here we have f. So this definition is done for all real valued x.
Yeah.
And so far there is no k involved. Then we take x, j, we define a bunch of points. So let's say now in our case this is f beautiful,
Yeah.
and something like this. This is A beautiful, F beautiful, something like that. And then we define a set of points in the interval between 0 and 1. So here is 0, here is 1, and then actually we choose k points here. So we take these points, and here j runs from 1 up to k. And then m tilde, the jth component of our measurement, m tilde, will be this stuff evaluated at that point.
Yeah. So basically, if this, you drew this should there be like some kind of like n tilde j? You know, no, not. I mean the third line.
Well.
I don't know. But
Yes, yeah, you're right. I mean, my notation is.
But I
yes,
the point now.
yes.
The point, yeah.
My notation is okay. My notation is bad. So this this should be called something. So this, let's say, a beautiful. This would be. This would be an operator from some function space, maybe some Lebesgue space on R to maybe some other Lebesgue space on R. So this is an operator between function spaces,
yeah.
And then with that notation, actually this A beautiful would be. Maybe from the same, or well, from the same function space, but the target space should be RK, and then we would define A without the tilde. We would define it with this formula. So yes, the notation is a little bit not so perfect.
Yeah.
Okay.
Yeah.
Cool.
Great.
And I think today, as usual, please do expect some confusion to happen. Especially now we are working with real data. That's always full of surprises. So we'll see how this goes. It may be that this becomes a disaster and nothing works, but we'll see. Maybe it's a learning experience even that way. Let's see what happens. Maybe this is too. So for efficiency reasons, I will shoot both targets in the same pictures. We will have the need to little bit modify them afterwards. So now what we need to do is let's see. Let's make a little plan. So we need to take several pictures. So we need to take a sharp picture just to kind of have our phantom and see how it is. And for comparison reasons, we should take sharp pictures and with ISO 100. So that means low noise. Low noise with ISO 100. And high noise with ISO 6400. And then we should take a little bit blurred one, then a little bit more blurred, and maybe even more. It's always kind of hard to say what will be practically possible to really recover so well. And in my experience, even a small amount of blur can cause quite a lot of trouble for us. So it's good to have a couple of options what to do. So let's shoot these 8 pictures, and I think it may be best to kind of first do one of these and then do both ISOs and then blur and do both ISOs and so on. So it involves a little bit of manual stuff here, but actually I think this should be a little bit lower. Let's put it lower. Okay. Let's see how it works. Something like this. And okay, ISO 100. Aperture, let's take 8. Just and let's take a 2-second shooting delay so that I won't move the camera with my hand. So when I push, so it takes 2 seconds and then it takes a picture. Let's see, it looks pretty okay, but let's see how the focusing seems to be pretty sharp. Okay, please come and take a look. Peek inside the camera here so